This is Unit 4.5, Global Wind Patterns. We're going to look at properties of air that determine circulation patterns, as well as properties of the Earth that affect circulation patterns. So first, we're going to look at four properties of air that determine air circulation. So the first thing you'll notice about air is that its density varies based on elevation. So if you're looking at this diagram on the left, yellow box says at sea level, you'll see there are a lot more, uh, not air molecules, but molecules of oxygen and nitrogen in the air. Whereas if you go up to 14,000 feet, there's a lot less oxygen and a lot less nitrogen, just the air is less dense. And so the thing that happens with air is that if it's less dense, it rises. And specifically, if you heat up the air, if you make it warmer, it becomes less dense and it rises. So if you remember back to the PowerPoint, 4.1, I was talking about density. Here it is again. If you make air warmer, it becomes less dense, and things that are less dense rise. Another property of air is its water vapor capacity. So, warm air has a higher water vapor capacity. If you've ever wondered why the humidity seems to be such an issue in the summer, but it's not in the winter, that's because in the winter, the cold air can't hold as much water vapor, and so it really can't get as humid. But in the summer, when the air is plenty warm, it gets plenty humid. Eventually, it can reach a saturation point, and that's where precipitation happens, of course. You can see kind of on the left this um, difference between what the water capacity is at 90 degrees Fahrenheit, which is pretty tropical, versus 40 degrees, which is pretty polar, like cold polar. And you can even see this graph on the right where it shows how the maximum water vapor capacity changes with temperature, right? It actually increases exponentially. Another property of air is what's called adiabatic heating and cooling. And so, as a certain amount of air, we're going to call it a parcel. As a parcel of air changes size, it also cools or heats up. So, let's say, start on the bottom left, you have a small parcel of air that's fairly warm. As it rises, it expands and it cools because it has the same amount of energy, but it's spread out over a larger area. Then conversely, if you take that larger parcel of air, but you condense it, right, you make it smaller, it starts to warm up. So as air rises and the pressure lowers, the air expands and it cools. And so that's what's called adiabatic heating and cooling. Finally, another property is the release of energy when water vapor condenses into precipitations. So this actually releases energy as heat. So let's say you have ice, solid water, liquid water, and then vapor, which is water in a gaseous form. There are different ways, different processes you can change between those forms, right? Vapor can condense to a liquid, which can freeze to solid. Vapor can also go straight to a solid, right? It can just be deposited the same way ice can become a vapor by sublimating. Um, but in order for ice to turn into vapor, it needs to take heat energy from the environment, right? That um, the energy you need to melt the ice has to come from the environment. Conversely, when you take water vapor and you solidify it, energy is released to the environment. So we see this most often when water vapor condenses into precipitation, it releases energy to the environment. So what we get when you take all these processes and you put them all together is you get a way for air to circulate in the atmosphere. So let's say you started on the bottom right corner where you have hot, wet air, right? You have this parcel of air at the surface. It's heated by the sun and it picks up water vapor. Because it's warmer, it can hold more water vapor. But as it rises, it expands adiabatically and it cools. And then that condenses the water vapor that it has. So we tend to see precipitation as that air rises and some heat that is released to space. Um, but then that air gets pushed in some direction, usually sideways. And it's cool and it's dry. And because of that, it starts to fall and it becomes compressed. And as it compresses adiabatically, right, it warms up. Then you've got some warm, dry air, which starts to pick up, water vapor because it's warm. It slides kind of over sideways, and then it becomes the hot, wet air. And so you get this convection cell, really, where the air is constantly circulating, picking up water vapor, having it precipitate out, cooling, and then falling and warming again. And so, where we see this most commonly, most clearly, is what's called the Hadley cells. Um, so at the equator, right, where things are the warmest, that's where the air tends to be heated up, and as it rises, it tends to precipitate. So at the equator, this is where we see a lot of tropical rainforests. This is where we see these Hadley cells form. And the Hadley cells are really kind of a mirror image of each other. There's one on the northern hemisphere and one on the southern hemisphere. And where the Hadley cells, where the cool air starts to sink is right around 30 degrees latitude, either 30 degrees north or 30 degrees south. And these latitudes are where you get a lot of dry air, where the air is sinking. And once the air reaches the surface, it kind of goes in either direction. It'll go north, back towards the equator, or it'll go south. And, fun name for the latitudes where that happens, that's the horse latitudes, where that air starts to move north. Now, notice that this happens in the troposphere. Right at the top of this diagram is the tropopause. So this is where the Hadley cells are. Now, the Hadley cells are not the only cells out there, and we're going to talk about those in a moment. If you want to do a step-by-step drawing, here's some steps for you. This is how the atmospheric circulation works. The warm, moist air near the equator becomes less dense and rises, and lower pressure results from the warm air rising. The water vapor cools and precipitates, resulting in heavy rainfall in those equator latitudes, or the equator. But then, having risen and cooled, the air moves towards the poles and away from the equator, where the pressure is higher up there, so it moves away from that pressure. The dry air cools as it moves towards the poles, and then around 30 degrees latitude, the air sinks, creating high pressure area, and then it goes from the high pressure area to low pressure area. So that's how the Hadley cell works. In fact, there's not just Hadley cells on the Earth. There's another cell that moves from like 30 degrees to 60 degrees latitude. Those are the Ferrel cells. And then the polar cells are, of course, at the top near the north and the south poles. And you'll notice how these convection cells sort of complement each other. Like where the Hadley cell sinks, the Ferrel cell is also sinking, and then the air moves either north or south. Where the Ferrel cell rises, the polar cell also rises. And then generally air at the poles is sinking. We can see the effects of these cells on biomes and the locations of those biomes. So notice how tropical biomes tend to be near the equator, right? If you're looking at South America, you're looking at the equator running through Ecuador and Brazil and maybe the north part of Argentina. But then parts of Africa that are near the equator are very tropical, as well as southern India and most of Indonesia, and maybe even a little bit of northern Australia. But then above that and below that tropical area, you get some really arid, dry places, southwestern US, North Africa, southern or South Africa, and also, most of Australia. So the convection cells in the atmosphere are responsible for a lot of what we see in terms of precipitation in those biomes. The other property that has a big effect on atmospheric circulation is the rotation of the Earth, and this results in what's called the Coriolis effect. So, as the Earth is rotating, the air moves at different speeds on the Earth depending on where it is. So, air at the equator is moving very fast in a circle, right? But as you go further north, the air is literally moving more slowly because the Earth up there is moving more slowly. It rotates at the same rate, but the actual distance that the air has to travel is much smaller. And so this results in air being deflected. Remember, in the Hadley cell, the air that rises from the equator then pushes north, but as it's being pushed north, it's moving faster than the Earth is rotating at that point, and that causes it to deflect. So the deflection depends on which hemisphere you're in. In the northern hemisphere, air is deflected to the right. In the southern hemisphere, it's deflected to the left. Whether you're moving north or south, it's always to the left, um, depending on which hemisphere you're in. So you can see here kind of like a 3D diagram where you see the Hadley cells and the Ferrel cells and the polar cells overlaid on top of the deflection from the Coriolis effect. And what this results in are these winds that have names from, back when boats had to sail using the wind. So you have like the northeast trade winds, the westerlies, southeast trade winds, and then also in the southern hemisphere, some westerlies. Another effect of the wind, so we've determined like how the wind patterns happen. One effect of the winds are what's called ocean gyres. So surface water in the oceans moves not necessarily because of ocean currents, but is actually affected more by the direction that the wind flows. So there's some amount of Coriolis effect in the ocean, but not quite as much as it is in the atmosphere. But then the wind patterns affect the circulation of the surface water in the oceans. So the five major gyres are the North and South Pacific gyres, the North and South Atlantic gyres, and then the Southern Indian Ocean gyre as well. And some of the effects of these gyres, like they can affect water temperature as cold water circulates south and becomes warmer. It can affect salinity of the water because the water temperature determines how much salt it can hold, and then also distribution of nutrients is affected by the circulation of these waters. All right, well, that is Unit 4.5, Global Wind Patterns. Please let me know what questions you have.